So here is an alternative way to compute expectation, which is often useful. Theorem. So maybe let me get the old definition in view so we can compare them. Before we were saying that we sum over the sample set of the probability of each outcome. But alternatively, we can sum over the outcomes, the outputs of the random variable. So sum over the elements of the image. And then the analog of the summand is that x of s is what we're calling r, which is our element of the image. And the probability of s corresponds to taking the probability that x takes the value r. So I don't mean that these are literally the same terms in these sums, but they're analogous, and the proof that we're going to show is essentially going to come down to rearranging them so that they match up. So this looks quite similar, but essentially it's just like a slightly different way of computing the expectation, which is sometimes more efficient because this set might be much smaller than this set, basically. So let's prove this really quickly. Like I said, the proof is essentially just rearranging the sum. So let's first recall what this thing means. We defined this to be the sum over the elements of the sample space that map to R of the probability of all of these outcomes. Now, let's start with our definition of the expected value. We defined it to be the sum over S in S, probability of S, times X of S. And now, we can rewrite this sum basically by splitting it into two parts. So now we're going to take the sum instead over the image of X, and then we're going to take the sum over the elements of S that map to that image. So essentially, this summation is the same as this summation. We've just written it differently. And the reason is that this version is essentially just breaking it up into smaller pieces corresponding to each element of the image of X. So we put our same summand on the inside. And now, if we focus our attention on this inside piece, we notice that this part, X of S, is constant because we are setting it on this sum, we're setting it to this value R. So let's see. So let's keep the sum R in X of S, and note that this part is R, and this part, So we can factor this out in front of the sum, since it's a constant. And then what's left in the sum, this part, is simply the probability that x equals r, as we see from our definition up here. So this simplifies to r times the probability of x equals r, and that is exactly the formula that we wanted to arrive at. So that completes the proof. So let's show an example of this new way of writing expected value. What is the difference? To try to make it concrete, let's compute the expected number of heads in 4 flips of a biased coin. So remember, this is sort of our prototypical binomial distribution. So consider S equals the set of strings of 4 coin flips, which we can model as 4 letters, heads or tails. These are the outcomes of flipping a biased coin. And let's say that the probability of heads is 2/3. So this is not a uniform distribution in particular. And x, the random variable on S, measuring the number of heads. So for example, what does x send the string HHTH? You just count the number of heads, and this maps to 3. So in this setup, x is the random variable measuring this experiment that we described, and we will recognize the distribution of x is a binomial distribution with n equals 4, the number of Bernoulli trials, and p equals 2/3, the success probability of each trial. And to point out the difference between the two formulas for expectation that we've written down, let me write them here. So the expected value of S is the sum over S in S, probability of S times X of S, or expected value equals sum over R in X of S, R times probability X equals R. And the difference, for example, in this case, one important difference is that you're summing over a different set, which basically makes, potentially makes your problem more or less work to solve. So in this case, you will note that this sum on the left has 16 terms, because the cardinality of S is, let's do that quickly in our heads. S is strings of 4 letters, H or T. So how do we count this? Well, we basically have 4 slots. We're using the product rule, right? Each of these 4 slots gets an H or a T, 2 options. So the number of total ways to do this is 2 times 2 times 2 times 2, which is 16. But on the other hand, in this sum, we are summing over the outcomes of X, and the outcomes of X are the number of heads in 4 coin flips, which is some numbers 0 through 4. So there are 5 of those possibilities, and there are 5 terms in this sum. So basically, this case is a much smaller sum, much simpler to compute than in this case. And that's why this other formulation can be useful. So let's go ahead and compute it. It's still going to be a little bit long to write out all of these terms on my little whiteboard here, but let's start. So let's say using this, we compute expected value of x is, so for each term, we want that value that x takes times the probability that it takes that value. So like we said, the possible values are 0 through 4. So let's start with 0. And then the probability that it takes this value, remember that x is gives us a binomial distribution with parameters n equals 4 and p equals 2/3. So let's remember our formula for the binomial distribution. It is n choose k times p to the k, 1 minus p to the n minus k. So we just replace n and p with n and p, and then k is the thing that we are summing over. So let me erase this and replace it with those numbers. So this is 4 choose 0, 2/3 to the 0, 1/3 to the 4th. And then the next outcome is 1. The probability is 4 choose 1, 2/3 to the 1, 1/3 to the 3rd. And now I'll put in some dots. And the last term is the outcome is 4. And the probability is 4 choose 4, 2/3 to the 4, 1/3 to the 0. And if you do add this all up, you will find that this is equal to 8/3. But let's take a moment to actually go back and think just intuitively about what we expect in this situation. We have a coin whose probability of heads is 2/3. So we expect it to come up heads about 2/3 of the time. So if we flip it 4 times, we expect it to come up heads about 2/3 of 4 times. And you'll note that this is equal to 4 times 2/3, which is exactly the intuition that we just described. So in general, it turns out that this is true. In general, if x is a binomial random variable with parameters n, the number of trials, and p, the success probability of each trial, then expected value of x is n times p. And this corresponds to our intuition, like we said. We expect success about p% of the time, where we're understanding p as a fraction. So this expectation matches our intuition. And again, we can see in this example that our intuition is essentially what we're trying to formalize in defining expected value, and it seems to be working well. Our results have been turning out exactly as we expect.